Okay, let's unpack this.
Let's do it.
Today, we are taking a fascinating and, I have to say, a highly technical detour into the engineering behind medical imaging. We're diving deep into the world of ultrasound simulation, specifically how engineers use, foundational physics and some really high-powered computation to create perfectly synthetic ultrasound data.
Yeah, and this isn't just about rendering a pretty picture. It's about modeling physical reality down to the sub-millimeter scale.
Right.
Our source material for this deep dive maps out a complete end-to-end technical stack. We're literally tracing the signal path, starting with the acoustic wave equation.
Fundamental physics.
Exactly. The thing that dictates how sound moves through human tissue. Then we move through this really complex multi-channel signal processing beamforming. And it all culminates in deploying those critical synthetic signals to train lightweight AI models.
And that really is the core of our mission today, isn't it? We want to abstract the mathematical and physical principles that govern ultrasound.
Understand the whole workflow.
The whole thing. From start to finish, how do you generate highly realistic synthetic B-mode and Doppler data? And then, and this is the really exciting part, see exactly how the simulation capability is not just some theoretical exercise.
No, not at all.
It's a blueprint that is enabling instantaneous real-time diagnostics via edge AI. It's a journey from, classical wave physics to cutting-edge silicon optimization.
And you'll see that the better we get at simulating reality, the better our AI models can actually diagnose it.
Okay, so let's ground ourselves in the fundamental physics that dictates, well, everything that follows. We are talking about sound waves, acoustic pressure, propagating through a medium.
In this case, soft tissue.
Right. And that behavior is governed entirely by the wave equation.
That's it. That's the starting point.
Yeah.
When you look at the fundamental relationship governing acoustic wave propagation, it's all summarized by this one equation. 1 client P, frafmin 2, frafmin 2 to ven.
Now, for listeners who might not be looking at partial differential equations every day, that can look pretty intimidating.
It can, for sure. But it isn't as scary as it looks.
So how do we translate that? How do we get an intuitive physical understanding of what that equation is actually saying?
It's actually a very elegant statement of equilibrium, of balance. The left side, that here to play is the T, Peter. That's called the Laplacian of pressure. All it's telling us is how the pressure is curving or changing spatially on the 3 dimensions.
Okay, so it's shape in space.
Exactly. And the right side tells us how the pressure changes over time. Specifically, it's about the rate of acceleration, and it's scaled by the speed of sound, citable.
So the equation is basically a law. It's saying the spatial curvature of the pressure wave must equal its temporal acceleration, scaled by the properties of whatever it's moving through.
You've got it. It is the defining rulebook for every single echo and every single transmission. There's no escaping it.
And you mentioned the properties of the medium. The most critical one for soft tissue ultrasound has to be that speed of sound. Some of it.
Precisely. While, different tissues do have slightly different acoustic properties.
Fat, muscle, liver, they're all a bit different.
They are. But for calculation purposes in clinical ultrasound, we have to adopt a standard. And that speed of sound, $, is standardized to approximately 1,540 meters per second.
And why is that standardization so important? Why not just use the exact value for each tissue?
Because that standardization it's non-negotiable in the engineering process. Every single time, delay calculation, the depth estimation, the focusing, everything, it relies entirely on this fixed velocity assumption.
So if the actual tissue in a patient's body was wildly different from 1,540 meters.
The image would be geometrically distorted, your measurements would be wrong, things would appear deeper or shallower than they really are. It would be chaos.
Let's talk about the scale this forces us to work within, because I think it really underscores the engineering challenge here. If we use a common operational frequency, something like, say, $5 expand to 5 millihertz, the resulting wavelength and timing are just minuscule.
They are tiny. And this is where the precision engineering really comes in. At 5 millihertz, the corresponding wavelength, which is just lambda, CFC-COO, is a mere 0.308 millimeters. Just think about that for a second. The element of physics that is responsible for your spatial resolution is shorter than 1/3 of a millimeter.
And that tiny wavelength is why ultrasound can offer such impressive axial resolution, the resolution in depth.
It is. If you were trying to find a sub-centimeter lesion, that 0.3 millimeter resolution is the difference between seeing it clearly and, well, just missing it entirely.
Okay, so that's the spatial scale. Now look at the temporal scale.
It's even more mind-boggling. The period $2, which is the time it takes for one full cycle of the wave, is just $100.
So for 5 megahertz, though.
That's zero point 0.2 microseconds, or 200 nanoseconds. Everything is happening at lightning speed. And to accurately capture and reconstruct this rapid oscillation digitally, we need an incredibly fast sampling rate, 5 hours.
And our sources suggest a really common sampling rate is 40 megahertz. Why that number specifically for a 5 megahertz signal? It seems like a lot.
It does, but 40 megahertz is exactly 8 times the carrier frequency. And this 8x oversampling gives you some significant benefits.
I mean, the Nyquist limit only says you need twice the frequency, right? So 10 megahertz should be enough.
In theory, yes. But sampling at 8x provides substantial numerical stability for all the signal processing steps that come later, especially when you're dealing with wideband pulses, which you always are. It also greatly simplifies the design of the digital anti-aliasing filters.
So what does that mean in practice? How many data points are you capturing?
It means we capture exactly 8 digital samples over the course of that single 200 nanosecond wave period. That gives us exceptional fidelity for the raw signal reconstruction.
And all this precision brings us directly to a computational problem.
A huge one.
If you're trying to simulate the interaction of a single wave front with, I don't know, thousands or even millions of tiny scatterers in a virtual phantom, keeping track of every interaction in the time domain is just computationally crushing.
It's basically impossible to do in real time, which is why we pivot. We pivot to the power of the frequency domain using the Fourier transform.
Fourier transform Zix XTEJ2, SPEJT DT da. It's the core mathematical tool here.
It is. It fundamentally converts a complex time domain signal into its component frequencies, 6 to us. And that transition is absolutely vital for simulation.
Why? What's the benefit?
Because many physical effects that are represented by these really complex time domain convolutions, things like geometric travel time or the filtering effect of attenuation, they are mathematically transformed into simple multiplications or phase shifts in the frequency domain.
Okay, can you elaborate on that a bit?
Yeah.
Why is a phase shift computationally so much better than a convolution?
Well, time domain convolution scales very, very poorly. If you double the number of data points you're working with, the computational time can increase by fourfold or even more depending on the algorithm. It's just incredibly resource intensive.
Okay.
In contrast, a geometric travel delay is just a time shift. We'll call it tau. In the frequency domain, a time shift becomes J2 pic tau. It's a simple, elegant, complex multiplication that you apply element-wise across all the frequency bins.
So you're turning a huge, slow calculation into a quick, simple one.
Exactly. This transformation is what fundamentally makes simulating complex physics across millions of data points tractable and, efficient.
Our source material really highlights this need for computational efficiency, especially when you're designing these simulation engines. And this leads us to something called the real FFT, or RFFT, as an essential optimization tool.
Yes, the RFFT. This is where signal processing theory meets hardware pragmatism.
What do you mean by that?
Well, the raw echo signals we are dealing with are real valued. They don't have an imaginary component in the time domain. Because of that, their frequency domain representation has a special property called conjugate symmetry.
And conjugate symmetry means?
It means the spectrum at negative power is just the complex conjugate of the spectrum at positive tether.
So if we know the positive half of the spectrum, the negative half is completely redundant. We already know what it is.
Exactly. The RFFT exploits this. We only need to compute and store the positive frequency components, plus the zero frequency DC component.
And in a typical DSP chip implementation, what does that get you?
It means you cut the required memory storage by roughly 50%. And you often achieve computation speeds close to 2 times faster than if you ran a full complex FFT. For an engineer designing a simulation that has to run millions of RF lines, it's a non-negotiable optimization.
Okay, so let's put this into practice. Let's trace the echo from a single tiny scatterer in the tissue. How do these frequency domain components combine to model the signal that's received by the transducer?
So we model the total frequency response from a single scatterer, let's call it CV-SU, as the product of 3 primary elements. First, you have the spectrum of the transmitted waveform itself, THEF.
So that's the shape and bandwidth of the pulse we send out.
Yep. Second, you have the travel time. That's the critical component.
Right.
The scatterer is at a distance $, so the round-trip delay is 2 AC deal. This delay manifests as that complex phase shift we talked about, G2PF.
And if the scatterer is deeper, tau is larger.
And the phase shift changes more rapidly with frequency. Finally, you have to incorporate the directivity of the probe. We'll call them ATX and DeVo-Do.
And that just accounts for the fact that the sound energy isn't a perfect point source, right? It's a beam that's focused or unfocused at specific angles for both transmit and receive.
You've got it. So that complex real-world process, sending a shaped pulse, having it travel, get attenuated, scatter, and then return, is just distilled into a series of simple multiplications in the frequency domain.
It seems like the ultimate simplification of physical modeling.
It really is. The total raw RF data spectrum, RF total, is simply the linear sum of all those thousands of individual scatter responses across all the transmit events and all the receive elements.
And once that total spectrum is built up and defined in the frequency domain,
We use the inverse RFFT to convert it back into the time domain. And that resulting time domain signal is it. That's the raw echo signal, or RF data, and it's ready for the next phase, beamforming.
okay, so we've simulated the perfect echo, but reality is harsh.
It is.
That sound wave loses energy dramatically as it propagates through tissue, and if our simulation is going to be realistic at all, we have to accurately model this decay. Our sources break this energy loss down into 3 distinct predictable pillars.
And these 3 losses are the physical limitations we are constantly fighting against in ultrasound system design. The first, and maybe the most universal, is geometrical spreading loss.
That was purely about geometry, right? The energy just spreads out.
Yes. For a point source, the acoustic intensity decays proportionally to the inverse square of the ejectance, so $102.
So if you double the distance, the intensity is quartered. It's inescapable.
Absolutely. And in the decibel scale, which is how we track these losses in signal processing, that decay translates to a loss that's proportional to $20 logs.
So just traveling from 1 centimeter to 2 centimeters causes a 6 dB loss just because of the geometry. It has nothing to do with what tissue it's passing through.
Exactly. It's distance dependent, not frequency dependent. But the second pillar of loss, that one is critically tied to frequency. It's frequency dependent attenuation.
And this is the thermal and viscous loss of energy that's actually absorbed by the tissue itself.
Right. This loss is exponential. And it's why choosing the right transducer frequency is basically the first decision a radiologist makes.
I see.
The pressure wave decays exponentially as it travels. The equation is based on alpha best over. The key here is that the attenuation coefficient alpha is directly proportional to frequency.
And the standard value for soft tissue is often cited as 0.5 dBcmm hertz.
That's the one. And this relationship is the core trade-off in all of ultrasound imaging.
Let's give a concrete example of that trade-off because I think it's really important.
Okay, imagine you are trying to image a large structure, like the liver, maybe 10 centimeters deep.
Okay.
If you choose a high-resolution 5 millihertz probe, the total two-way attenuation would be, let's see, 0.5 times 5 millihertz times 10 centimeters times 2 trips. That's 50 decibels loss.
50 decibels. That's a massive amount of signal decay.
It's huge. But if you drop down to a 2.5 millihertz probe to get more penetration, the loss halves to 25 millimeters. You get a much, much stronger signal back.
But you sacrifice that beautiful 0.3 millimeter resolution you had with the 5 millihertz probe.
That's the trade-off. It's unavoidable. And simulation engines have to model this attenuation perfectly to match what happens in reality.
Okay, that makes sense. Now for the third, and maybe the most subtle pillar, Rayleigh scattering. This doesn't just reduce energy, it dictates the actual texture of the image.
It really does. Rayleigh scattering governs that granular textured appearance that we call speckle, which is characteristic of healthy tissue.
And this happens when the scatterers, the microscopic imperfections and boundaries within the tissue, are much, much smaller than the wavelength.
Right, when lambda is in. And the truly remarkable mathematical property here is the power dependence. The scattering power is proportional to 5/4 boulders.
To the 4th power, that is a staggering relationship. So if you double the frequency, the scattering power increases by a factor of 16.
Yes, it's a huge jump. And this steep 4/4 to dependence is exactly why high-frequency probes like a 12 or 15 millihertz probe create these incredibly detailed, finely textured images of superficial structures, like plaque in an artery or superficial veins.
Because they're able to generate a massive amount of backscatter from those tiny structures.
A massive amount.
Yeah.
But of course, those waves also attenuate extremely quickly because of that 0.5 dBcm millihertz rule, so their penetration is very limited.
So having suffered this massive decay and scattering, the weak signal finally arrives back at the array of transducer elements, often barely distinguishable from the electronic noise. This is where delay in some beamforming, or DAS, performs its, I think you could call it a heroic task of retrieving a coherent signal.
Indeed. DAS is really the masterpiece of ultrasound signal processing. The whole concept is alignment.
Okay.
You have, say, 32 or maybe 64 separate signals, 60 coming back, one to each element.
Yeah.
And you assume the signal originated from a specific focal point in the tissue. We'll call it 6SS, CFS.
All right.
Then you calculate the exact necessary time delay for the signal to have traveled from that single point to reach each individual element.
And then you digitally shift all the signals in time, aligning them precisely, and sum them up coherently. The formula is Freighton's sum, and that's SOLAS.
And the complexity lies entirely in that delay calculation. Trials is calculated geometrically based on the element position 6S, the target focus point 6S, ZFS, and of course our old friend, the speed of sound staller.
And the goal is that when you sum them, if the energy truly came from that focus point, all the signals align perfectly and you maximize the amplitude.
That's the idea. But if the energy came from noise or from an echo from an off-axis direction, what we call a side lobe, the signals arrive at the elements slightly out of phase.
They're not aligned.
Exactly. So when you sum those off-axis incoherent signals, they tend to cancel each other out destructively.
And that's the magic of DAS. It selectively reinforces the signal you want, while simultaneously suppressing everything else.
It is. And this leads to the massive increase in quality that we call beamforming gain.
How do we quantify that? What's the magnitude of the improvement in the signal-to-noise ratio, the SNR?
The quantification is actually very powerful. The desired signal, because it's perfectly coherent, increases linearly by the number of elements. So if you have 32 elements, the signal amplitude increases by 32 times.
Okay.
But the unwanted electronic noise, that's random and incoherent. So it only increases by the square root of $9. So squared ovoid, which is about 5.6.
So the signal gets a much bigger boost than the noise.
A much bigger boost. The resulting SNR improvement is calculated in dB as $20 old dog.
So using our example of a 32-element array, $20 log gives us approximately 30.1 dBb of gain.
It's a phenomenal leap in signal clarity.
It's exponential. A 30 dB gain means you've multiplied the power ratio of the signal to the noise by a factor of 1,000.
It is. It transforms an echo that was deep, weak, and probably lost in the electronic noise floor into a clear, bright data point that's suitable for diagnostic imaging. Without this fundamental concept, clinical ultrasound just wouldn't work at the depths we needed to.
All right, we have established the complex physics and the signal processing required to take a weak, noisy RF signal and turn it into a high-fidelity, coherent RF line. Now, we stitch this all together into the end-to-end B-mode synthesis workflow. This is the process that turns mathematical output into a visual image.
Right. The simulation workflow involves 6 distinct stages, moving from defining the physical world to the final display. It starts, of course, with definition. So step 1, define the probe.
And for our synthetic data, this means defining the size like 64 elements, a 30.0 millimeter aperture, and the acoustic properties like a buzzer of 5 millihertz.
Correct. Step 2 is to define the scan strategy. This is the geometry of how we're going to interrogate the tissue.
What's a common strategy for that?
A really common strategy used in modern ultrasound simulation and in real machines is plane wave compounding.
Okay, what is that?
Instead of steering a narrow focused beam for every line, we transmit multiple wide unfocused plane waves, maybe 5 of them, angled between, say, minus 15 degrees and plus 15 degrees.
And then you combine the results.
We synthesize the final coherent image by summing the received echoes from all 5 of those angles. This compounding technique is hugely important because combining multiple views significantly improves the contrast and reduces that speckle noise we were just talking about.
Okay, so after the probe and the scan, we have to define the virtual environment itself. Step 3, define the phantom.
The phantom is our virtual tissue. We define the precise coordinates, the x and z, and the reflective magnitude of all the scatterers within our simulation volume. For example, 64,000 scatterers randomly placed in a grid from 10 to 35 millimeters deep.
And this virtual scatterer map is the ground truth. It's the perfectly clean target for our simulated sound waves.
It is. So once everything is defined, the engine performs step 4, generate RF data.
This is the computational heart of the whole thing.
It is. As we discussed, the simulation engine calculates the raw time domain echo from every single element for every single transmit angle.
Yeah.
It does this efficiently in the frequency domain and then converts it back using the inverse RFFT. The result is just this massive multi-dimensional array of high-frequency raw RF signal data.
And step 5 is the processing core. We take that raw data, we beamform it to create our coherent scan lines, and then we hit a really crucial digital signal processing step, extracting the envelope.
This is a critical transition. The raw RF signal is an oscillating cosine wave that's modulated by an amplitude.
Right, it goes up and down really fast.
It does. And that high-frequency carrier wave itself, the 5 megahertz part, carries no diagnostic information. The diagnostic information, the strength of the echo, is carried only by the low-frequency envelope. 8 wraps around that wave. We have to isolate 8 ping.
And mathematically, this isolation is achieved using the analytic signal, which is derived via something called the Hilbert transform. This is where it gets very technical, but it's an essential piece of DSP.
It is. The analytic signal, we call it ZST, is defined as the original signal, CT, plus an imaginary component that's created by shifting the signal by 90 degrees. So ZSDSXT plus JHST.
And that dollar is the Hilbert transform, which does that perfect 90-degree phase shift across all the frequency components.
That's right.
Let's try to make that a bit more intuitive. Why does creating a 90-degree phase-shifted imaginary twin of our signal actually help?
Okay, think about a circle. If you have your signal sum t, which is your cosine wave, and its 90-degree shifted version, which is a sine wave, by combining them as a complex number, ZST, you are essentially tracking the signal as it moves around a unit circle in the complex plane.
Okay, I'm with you so far.
The key realization is that the magnitude of this complex signal, which is Z la TT, is mathematically guaranteed to be the envelope. You have effectively stripped away all the high-frequency carrier information, leaving only the amplitude modulation, the echo strength, behind.
So it's a clever mathematical trick to isolate the information we actually care about.
It's a very clever trick.
So once we have that linear amplitude envelope, we are immediately confronted with the massive dynamic range problem.
This is the third part of the processing step, log compression. As we mentioned, the difference between the strongest echoes right near the probe and the weakest echoes deep in the tissue. It can span an amplitude ratio of 1,000,000 to 1 or even more.
So if you just displayed that linearly,
the deep tissue would look pitch black and the near field would be blinding white. You wouldn't be able to see any discernible detail.
it's like trying to take a single photograph that perfectly exposes both the inside of a dark cave and the bright midday sun outside. You can't do it. It requires compression.
Exactly. And the compression uses the logarithmic scale because human perception, our hearing and our vision, operates logarithmically. Log compression maps that huge linear range onto a usable grayscale by taking the logarithm of the ratio of the amplitude.
The equation being 1 TA max plus epsilon.
Right. And the 20 log ensures the output is calculated in decibels, the power ratio scale, which is essential for translating acoustic power into visual contrast that our eyes can understand.
And practical systems finalize this by selecting a constrained window, a specific range.
Yes. They clip the final displayed range to a standard dynamic window, typically something like negative 60 dB to 0 dB. This 60 dB window is what defines the contrast and the visual appearance of the final B-mode image. It ensures that the critical structural details in both the bright and the dark regions are visible to the human eye.
And step 6, of course, is the final visualization, where these process stand lines are interpolated and displayed as the familiar B-mode image we all recognize.
That's the end of line.
The B-mode image is absolutely crucial for anatomy, but ultrasound offers a unique capability in medicine, visualizing movement, especially blood flow. And this brings us to Doppler processing, which is our primary tool for measuring velocity.
Doppler fundamentally relies on the Doppler shift, which we call fifth day. When our sound wave reflects off of moving scatterers, like red blood cells, the frequency of the returning echo is shifted. And that shift is proportional to the velocity, $5 of those scatterers relative to the probe.
The resulting velocity equation, Vival-Fact.CFD, contains a really critical term that causes the most diagnostic headaches, which is the beam flow angle, cos theta.
Oh, that angle dependence is the Achilles heel of quantitative Doppler. It really is. If the ultrasound beam is perfectly parallel to the blood flow, then theta is 0 and theta is 1,1.
And the measurement is highly accurate.
Highly accurate, the shift is maximized. But if the beam is nearly perpendicular, so theta is close to 90 degrees, then cos theta approaches 0.
And since cosine is in the denominator of that equation,
small changes in your angle measurement lead to massive, completely unpredictable errors in your velocity estimate.
So even if the blood is flowing at a constant speed, if the clinician just slightly misaligns the probe, the displayed velocity could be wildly off.
Wildly off. This forces clinicians to always target angles well away from 90 degrees. They typically aim for something between 30 and 60 degrees, and then they have to manually input a correction angle to account for the known geometry of the vessel.
And the simulation engine has to replicate this angle sensitivity perfectly, I assume, to train users and AI models on the effects of misangulation.
Has to, yes.
The other major practical limitation that's imposed by the system hardware is aliasing.
Aliasing, yes.
Yeah.
This is tied directly to the pulse repetition frequency, or PRF, which is just the rate at which we transmit pulses.
Okay.
To measure motion, we need multiple pulses to estimate the frequency shift. But according to the Nyquist theorem, the maximum Doppler shift we can accurately measure is limited to half the PRF.
And this translates directly to a maximum measurable velocity, the Nyquist limit, VRF for Kazan data.
It does. And the choice of PRF has a huge impact on clinical practice. Well, the PRF is limited by how quickly the signal can return, the round-trip time. So if you want to look deeper into the body, you have to wait longer for the echo, which means the PRF must be lower.
And a lower PRF means a lower maximum measurable velocity.
Right. So if the blood flow exceeds this limit, say during peak systole in a really narrow stenotic artery, the signal aliasis, it wraps around.
Meaning a high positive velocity incorrectly displays as a high negative velocity.
Exactly. And that could potentially lead to a misdiagnosis of the flow direction or the severity of the stenosis. It's a serious artifact.
We use Doppler in two primary modes. First, there's the real-time, more qualitative approach, color Doppler.
Color Doppler is all about spatial mapping and speed. It uses an algorithm called the autocorrelation method, specifically the lag-1 correlation, to rapidly estimate the mean Doppler frequency within each pixel.
And then that mean frequency is converted to a velocity and mapped to a color scale, which gets overlaid on the B-mode image.
Yep. Conventionally, it's red for flow towards the probe and blue for flow away. It sacrifices the fine detail of the velocity spectrum for a real-time visualization of where the flow is and which way it's going.
In contrast to that, we have spectral Doppler, which sacrifices real-time spatial coverage for incredibly high temporal and velocity resolution.
Spectral Doppler is the quantitative workhorse. We place a small sample gate over the area of interest, like a major artery, and transmit a sequence of pulses. Then we perform an FFT across that sequence of pulses, what we call the slow time sequence. This generates a spectrum that plots the distribution of all the velocities, all the frequencies present in that sample volume over time.
And this is invaluable for characterizing flow dynamics, right?
Yeah.
Detecting turbulence.
Yes, turbulence shows up as spectral broadening, or it's used for calculating precise flow metrics like resistive indices in the kidneys. It's the detailed quantitative tool.
Now, moving beyond blood, we can also track the motion of solid structures using M mode or motion mode.
M mode is a really clever trick to maximize temporal resolution. You fix the ultrasound beam along one single line in the tissue.
So you're not scanning a whole area.
No, just one line. And instead of creating a 2D image, you repeatedly calculate the A line, which is just amplitude versus depth, at an extremely high temporal rate. Then you stack these A lines side by side over time.
And the resulting display is an image where the vertical axis is depth and the horizontal axis is time.
Correct. This allows for highly accurate measurement of the timing and extent of movement.
And where is this used most often?
It's used extensively in cardiology to track the rapid, characteristic sinusoidal movements of heart valves, like the mitral valve, or to calculate things like ejection fraction. It gives engineers and clinicians a clear, temporal signature of movement that standard B-mode imaging, which updates far more slowly, simply cannot capture.
Finally, we can move from 2D and 1D visualizations to volumetric imaging, 3D and 4D reconstruction.
This represents a massive computational leap. It requires defining a volumetric grid voxels, essentially, and performing that complex DAS beam forming across 3D delays instead of just 2D.
And 4D is just adding time to that.
4D simply adds the temporal axis to that 3D volume, allowing us to see movement in real-time space.
And I assume compounding is often utilized here as well.
Yes. Volumetric compounding involves acquiring data from multiple different angles or different elevational slices across the volume and then coherently summing them. This is absolutely necessary in 3D and 4D because combining those views dramatically improves the contrast resolution and provides the final essential step in reducing speckle noise throughout the entire volume.
Okay, We have spent the first 4 phases of this deep dive establishing the incredibly complex, physics-driven pipeline required to create ultrasound data. Now we arrive at the modern application of all this simulation power, creating perfectly labeled synthetic data to train the next generation of medical AI.
Right.
And this intelligence is moving out of the cloud and onto the device itself. This is the realm of edge AI.
And that shift to edge AI is really being driven by two unyielding forces in healthcare: latency and access.
Let's start with latency. We need instantaneous diagnostic feedback.
Absolutely. By deploying the AI engine directly onto the portable ultrasound device, you cut out the internet bottleneck entirely. This ensures extremely low latency, ideally below 50 milliseconds per frame.
And that 50 millisecond threshold is crucial, isn't it? It ensures the system doesn't feel sluggish. It allows for true, real-time feedback.
Like automatically tracking a needle during a biopsy or instantly calculating the volume of an organ as the user is scanning.
It also addresses the access problem.
It does. Portable ultrasound is often used in remote clinics or in ambulances, where cloud connectivity is either non-existent or just unreliable. The engine has to be robust and practical.
Which means it has to meet these extraordinarily tight constraints. Low memory footprint.
Typically between 50 and 150 megabytes of RAM.
And highly efficient operation, often relying solely on the device's main CPU, with GPU acceleration being, optional. So, given these severe constraints, how do engineers design deep learning models that can survive and thrive at the edge? You can't just throw a massive server-class network at it.
You can't. The model design strategy has to focus intensely on compactness and on multitask learning.
Okay.
We select lightweight neural network architectures known as efficient encoders, things like MobileNet v3 Small or EfficientNet Lite. These backbones are optimized for mobile computing through the use of design principles like depth-wise separable convolutions, which drastically reduce the computational load compared to traditional convolutional networks.
And once you have that efficient backbone extracting the core features from the B-mode image, the model needs to perform multiple tasks simultaneously to maximize the use of those resources.
Exactly. So we employ separate heads that are connected to that lightweight feature extractor. A UNet-Lite segmentation head, for instance, might focus on tasks requiring localization, like drawing the precise boundaries of organs or generating masks for detected lesions.
And at the same time,
Simultaneously, a classification head might analyze the exact same features to provide a scalar output like an anomaly score or risk prediction, identifying if a lesion looks benign or suspicious.
beneath the hard latency and memory constraints of edge AI, aggressive optimization techniques are absolutely mandatory. Our sources highlight quantization as maybe the most powerful lever here.
It is. Quantization is the fundamental process of reducing the numerical precision of the model's parameters and its activation values. Standard training uses 32-bit floating point numbers, or FP32,
And we convert these two.
to much lower precision. Most commonly, 8-bit integers, or INT8.
That is a 4-fold reduction in numerical storage, just going from 32 bits down to 8 bits. What are the engineering consequences of making that shift?
The consequences are massive speedups and size reduction. By converting the model to INT8 using a process called post-training quantization, the model size shrinks by over 50%. The example cited in our materials shows a model shrinking from 0.28 megabytes in FP32 down to just 0.12 megabytes in INT8.
That's a huge reduction.
It is. And more critically, INT8 operations are vastly faster on CPUs and on specialized hardware accelerators because they require less memory bandwidth and simpler arithmetic logic units, or ALUs.
But surely going from 32 bits of precision all the way down to 8 bits introduces a risk of losing accuracy.
It absolutely does. And that is the tightrope walk of edge AI. Aggressive quantization can lead to a slight degradation in diagnostic performance.
So what do you do about that?
Well, engineers have to carefully calibrate and validate the quantization process. Techniques like quantization-aware training or just meticulous post-training validation are required to ensure that the gain in speed doesn't compromise the safety or the efficacy of the diagnostic result.
What other optimization strategies are employed to squeeze every last ounce of performance out of these engines?
We rely on compiler-level optimizations like pruning, where model parameters that are deemed least important for the final output are just removed, and layer fusion, where sequential operations, say a convolution followed by a batch normalization, are combined into a single faster operation.
And of course, model distillation.
Yes, distillation is where the simulation power truly converges with the AI deployment.
Tell us more about this teacher-student dynamic.
Model distillation is the process of training a small, compact student model to reproduce the outputs of a much larger, high-performing teacher model.
And that teacher model might be FP32, trained on massive server-class GPUs using millions of our synthetic data points.
Exactly. And instead of training the student model purely on hard labels, this is a tumor, this is not, the student is trained to match the soft probability outputs of that massive teacher model.
So you're teaching it the nuance, not just the final answer.
You are. This allows the small quantized student model to maintain the high diagnostic fidelity of the massive teacher model, but without incurring all the computational and memory overhead.
It's how you get high-end diagnostic performance on a battery-powered tablet.
Precisely. The ultimate goal is to ensure that all of this complex physics, modeling, and deep learning optimization leads to clear, actionable clinical output for the end user.
So what does the clinician actually see? What's the final output of this highly optimized pipeline?
The final pipeline processes the raw B-mode frames, runs the lightweight model in real time, and converts the machine's output into structured graphical findings. This includes calculating and displaying contours of anatomical structures, performing standardized measurements like organ dimensions, and outputting structured findings reports.
And perhaps most importantly for clinical adoption, the overlays that build trust.
Absolutely. Explainability is paramount. We see the use of techniques like GradCam, which stands for Gradient-Weighted Class Activation Mapping.
And what does that do?
The AI system generates a heat map that gets overlaid on the B-mode image. This heat map highlights exactly which pixels or regions of the ultrasound frame most strongly influence the AI's diagnostic decision, like an anomaly classification.
So it shows its work.
It shows its work.
Mm-hmm.
And by showing the clinician the evidence the machine used, we dramatically increase the confidence in the utility of the automated diagnosis.
We have completed the deep dive. We've traced the signal path all the way from acoustic physics through the computational elegance of frequency domain simulation and precise beamforming to the final visual and diagnostic output. It is just remarkable how this entire physics stack now serves as the foundation for powerful, miniaturized edge AI diagnostics.
The synergy is undeniable. The ability to generate unlimited, perfectly characterized synthetic data that is noise-free and perfectly labeled, that is the fuel driving the rapid iteration and validation required for these complex, compact AI models.
So we need the perfection of the synthetic world to teach the AI how to handle the imperfections of the real world. That's it.
We've discussed how the trade-offs between frequency and resolution are just inherent in the physics. We detailed the computational heroics required to convert a weak echo into a clear B-mode image, and we explored the engineering compromises necessary to shrink a complex deep learning model down to a few megabytes.
So as we look to the future, where simulation and AI are becoming increasingly intertwined, what is the ultimate provocative consequence of being able to perfectly simulate reality?
Well, we started by needing to simulate ultrasound physics perfectly, just to understand the physics that governs the real world. Now, with AI, we use these incredibly detailed simulations to build virtual training grounds. And it makes you ask this profound question.
Which is,
how far can AI push the limits of resolution and diagnostic accuracy before we start relying entirely on the synthetic data we create, data that is perfectly clean, perfectly labeled, and free of all acquisition noise to validate our models, rather than relying on the noisy, messy, and fundamentally imperfect real-world acquisitions we're accustomed to?
so you're saying the simulator itself is becoming the standard?
It's becoming the gold standard.